In episode 54, titled Non-Stationarity Beyond Time Series, Drifting Patterns in Real Systems, we focus on drift as a practical reality. The rules that generated yesterday's data can change, and when they do, yesterday's model can quietly become today's liability. Many people associate non-stationarity only with classic time series, but in real systems, distribution shifts and relationships happen everywhere, even when the dataset is not framed as a time series problem. The exam cares because it tests whether you recognize when a model's assumptions about stable patterns are unsafe, and whether you know what operational safeguards reduce surprises. In cybersecurity and analytics work, drift is not an edge case. It is a normal outcome of changing environments, changing incentives, and changing adversary behavior. If you can describe drift clearly, you can design evaluation, monitoring, and response plans that keep models trustworthy over time. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Non-stationarity means that distributions or relationships change, so the statistical properties you learned in one period do not necessarily hold in another.
A stationary setting is one where the data generation process is stable enough that averages, variances, and relationships are consistent within the time horizon you care about.
Non-stationarity breaks that stability, which means the same feature value can become more or less common, or the same feature-outcome relationship can become stronger, weaker, or reversed.
The key is that non-stationarity is not just noise, it is structured change, and structured change requires structured response.
The exam often signals non-stationarity through language like recently changed, new policy, new product, or attackers adapted, and those phrases are hints that the underlying distribution is shifting.
When you recognize non-stationarity, you stop treating poor performance as a tuning problem and start treating it as a moving target problem.
Data drift is the first major category, and it refers to feature distributions shifting over time. In plain language, data drift means the inputs are changing, such as users behaving differently, devices changing, traffic patterns shifting, or measurement coverage evolving. A model trained on earlier data can then face new combinations of values or a new prevalence of certain patterns, causing performance to drop even if the true relationship between features and outcomes has not changed. Data drift can be gradual, like slow adoption of a new device platform, or abrupt, like a sudden change in logging configuration that changes how fields are populated. The exam may describe that the model suddenly sees more missing values or new categories appear, which are classic data drift signals. When you narrate data drift, you are describing change in what the model sees, not necessarily change in what the world means. Concept drift is the second major category, and it refers to the target relationship changing with context, meaning the mapping from inputs to outcomes evolves. In concept drift, the inputs may look similar, but the meaning of those inputs, or the way they predict outcomes, changes because the system's behavior has shifted. This can happen when attackers change tactics in response to defenses, when users learn and adapt to policies, when business processes change, or when product features alter the pathways that lead to outcomes. Concept drift is often more damaging than data drift because it means the model's learned relationships can become actively wrong, not merely less calibrated. The exam will hint at concept drift when it says something like, previous indicators no longer predict incidents, or the relationship reversed after a policy change, which is a direct clue that meaning has changed. When you narrate concept drift, You are describing a change in the rules that connect causes and effects, not just a change in the frequency of inputs.
Many forces can cause drift, and the exam expects you to recognize several common drivers that show up across domains. Seasonality is one driver, because repeating cycles shift distributions and can also shift relationships, such as different behavior on weekends or end-of-quarter periods.
Policy changes can change incentives and workflows, which changes both inputs and outcomes, sometimes immediately and sometimes with lag.
Product shifts can introduce new user journeys, new defaults, and new failure modes, changing what data looks like and what outcomes represent.
Adversaries are a uniquely important driver in security settings because they adapt to controls and detection, intentionally reshaping signals to evade models and exploiting blind spots created by fixed assumptions. When you can name these causes, you demonstrate exam-ready intuition that drift is not mysterious. It is what you should expect when systems evolve and actors respond.
Time-aware splits are a critical technique because they help you detect drift before deployment surprises by evaluating models in a way that reflects how they will be used. Random splits mix past and future, which can mask drift by letting the model train on patterns that appear in the evaluation period, creating an overly optimistic performance estimate. A time-aware split trains on earlier periods and evaluates on later periods, forcing the model to confront change and revealing whether its performance degrades as the environment evolves. This is not only a time series method, it is a general validation method whenever the data generating process can drift. The exam often tests this by offering a random split as an easy answer and a time-based split as the correct answer in a drift-prone scenario. When you choose time-aware evaluation, you are acknowledging that the future is not just more of the past and that honest validation must respect ordering. Monitoring is the operational counterpart to time-aware evaluation because even the best validation cannot predict all future changes and drift can emerge after deployment. Monitoring key features means tracking distributions, missingness rates, category appearance, and summary statistics over time, looking for shifts that indicate the input space is moving. Monitoring performance metrics means tracking error rates, calibration, false positive rates, and segment-specific outcomes, because performance drift is often the earliest sign that the relationship has changed. The exam expects you to understand that monitoring is not a luxury. It is how you preserve validity when the world changes. A strong approach includes both input monitoring and outcome monitoring because you can drift in inputs without immediate performance collapse, and you can drift in relationships before input distributions look obviously different. When you narrate monitoring, you are describing an early warning system for model health. Retraining triggers translate monitoring into action, and the exam often tests whether you can define triggers in terms of thresholds and business tolerance rather than vague feelings. A trigger might be based on a shift in a key feature distribution, such as a sharp rise in missingness or a new category frequency, because that indicates the model is operating in a new input regime. A trigger might also be based on performance, such as a rise in false positives beyond an acceptable operational load or a drop in detection rate below a safety threshold. The right thresholds depend on business tolerance because the cost of degraded performance differs across use cases, and the exam expects you to tie triggers to consequences. Retraining should not be constant, because constant retraining can chase noise and create instability, but it should be responsive when drift creates real degradation. When you describe retraining triggers well, you are treating model maintenance as a controlled process rather than a reactive scramble.
Segmentation by time period can help isolate changing behavior because it allows you to compare distributions and relationships across distinct eras rather than averaging change away. If you suspect a policy change altered behavior, you can segment pre-change and post-change periods and examine whether feature distributions or feature outcome relationships shifted. Segmentation can also reveal that drift is not uniform, such as when some regions drift earlier than others, or when certain user tiers respond differently to product updates. This is an extension of conditional reasoning, but with time as the conditioning variable, which makes it especially useful for diagnosing non-stationarity.
The exam often frames this as comparing cohorts or time windows, and the correct reasoning is to treat time as a source of heterogeneity rather than as a nuisance.
When you segment by time, you turn drift from a vague suspicion into a structured hypothesis about when and how the system changed.
A common and costly mistake is assuming yesterday's model works forever without monitoring, because that assumption treats models as static artifacts rather than as components in living systems. Even when the initial deployment is successful, environments evolve, new features are introduced, user behavior changes, and adversaries adapt. And without monitoring, you will learn about failure only when harm has already occurred. The exam cares because this is a governance and reliability issue, not just a technical one, and it often appears in scenario questions about operational risk and maintenance responsibility. A model that is not monitored is effectively unmanaged risk because it can silently degrade and still produce outputs that look authoritative. When you reject the set it and forget it mindset, you are demonstrating a mature understanding that model performance is a moving target in real operations. That mindset is essential in security contexts where drift can be intentionally induced by attackers to evade detection.
Communicating drift risk to leaders is part of operational reality because drift implies ongoing maintenance, not a one-time project deliverable. Leaders often want a model to be treated like software that can be installed and left alone, but drift means the model needs monitoring, retraining plans, and clear ownership. The communication should frame drift as expected change in inputs or meanings, not as a failure of the team, because setting that expectation reduces panic when performance shifts. It should also clarify what indicators will be monitored, what thresholds trigger action, and what the response options are, so leaders understand that the system has controls and that degradation will be detected early. The exam tests this indirectly by asking how to ensure continued performance, and the correct answers often involve monitoring and lifecycle management rather than additional model complexity.
When you narrate drift communication well, you are building trust by explaining both capability and limits.
Rollback and fallback strategies are essential because drift can break performance faster than retraining can safely restore it, and you need a plan for that gap. A rollback strategy means you can revert to a prior stable model or configuration if a new model or updated pipeline performs worse under current conditions. A fallback strategy means you have a safe alternative decision rule, threshold, or manual process that can be used when model outputs are unreliable or when monitoring indicates degradation. These strategies are especially important in high-stakes settings because continuing to operate on degraded predictions can create harm, false confidence, and operational overload. The exam expects you to consider safety and continuity, not just improvement, because the responsibility of analytics includes avoiding preventable failure modes. When you include rollback and fallback in your narration, you are treating drift as an operational risk that must be managed with resilience, not just with retraining. A useful anchor memory for this episode is drift changes inputs or meanings, monitoring catches it. Inputs changing corresponds to data drift. Meanings changing corresponds to concept drift. And monitoring is the mechanism that detects both before they cause sustained harm. The anchor also reminds you that drift is not always visible in a single metric, because inputs can drift quietly and relationships can drift without obvious input shifts. Monitoring should therefore include both feature distribution checks and performance checks, so you can detect early warning signs from either side. The exam rewards this framing because it shows you understand drift as a life cycle property, not as a one-off anomaly. When you keep the anchor in mind, you naturally choose time-aware validation, monitoring, and action triggers as part of any model deployment plan. To conclude Episode 54, name a drift type and then state one monitoring signal, because this is the simplest way to demonstrate you can diagnose and respond. If the drift is data drift, a clear monitoring signal might be a rising missingness rate in a key feature, or the sudden appearance of new categorical values that were rare or absent during training. If the drift is concept drift, a clear monitoring signal might be a sustained increase in false positives or a drop in true detection rate for a stable input distribution, indicating the relationship between features and outcomes has changed. In either case, the signal should be tied to a threshold that reflects business tolerance, because the point of monitoring is to trigger timely action, not to collect dashboards. When you can name the drift type and a credible monitoring signal, you show exam-ready understanding that non-stationarity is expected, detectable, and manageable with disciplined operational practices. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.